Thank you for joining me in this session. I will be sharing some recent results around threshold optimal ECDSA. Before I talk about that, I'd first like to take a moment to introduce myself. So my name is Michaella, and I work in a research team at a company called nChain. We do scientific research in many topics, predominantly around blockchain and cryptography. So today I will be sharing some of our recent results in cryptography. I would like to take a moment to thank my colleagues for help with the review process and the benchmarking. I would not have been able to do this without them. So moving on to threshold signatures then. So they're a type of digital signatures, and digital signature is created using a private key on a message. And what that does with the private key is that you end up with this single point of failure. The private key presents a single point of failure. So that has a risk of loss or attack. If someone loses their private key, then they're no longer able to create a digital signature. And if the private key is compromised, then the attacker could create a signature on behalf of the other person. So there's been a lot of interest around digital signatures, and particularly threshold signatures, because of blockchain technology. So in particular, and the reason why I was looking into it, a lot of blockchains utilize the ECDSA signing algorithm. So there's been around 17 threshold signature schemes for ECDSA. So the first one was in '96. And that was a great innovation, although it wasn't able to do all possible cases. And so people were looking to improve upon this scheme. The first thing that people wanted to do was create 2 of n schemes. So the '96 scheme was not able to do such a thing. And so a few results are around creating a 2 of n scheme. And then many of the results since then have are looking to find a general T of n scheme, which is also threshold optimal. So I'll come back to what exactly that means in a few slides. But I just want to point out that since blockchain technology was first created in 2009, you see that this is really where we see the majority of the threshold signature work from 2016 onwards until now, in the last 5 years. So it really has reignited a lot of the interest. The scheme that is presented today, that will be presented today, offers these contributions. So the first thing is low computational complexity. So it's the first threshold optimal scheme without any expensive computation, such as homomorphic encryption and zero-knowledge proofs. Then it also offers a low number of communication rounds. So there are 4 in total in the signing protocol and 2 in the key generation protocol. And the signing protocol matches another scheme that exists in terms of number of rounds. And the key generation protocol is 1 fewer than that same scheme. So it's a slight improvement upon that. Then the next thing it offers is a non-interactive threshold optimal signing round. So what the signing protocol does is it's split into 2 stages. The first is pre-signing, and the second is this final non-interactive round of signing. This scheme is the first threshold optimal scheme that offers in the final round of signing that none of the signers are predetermined. So in the final round of signing, any of the participants in the threshold scheme are able to contribute to that signature. That means that it offers some protection against failures of a certain number of participants. And this is the first scheme that has that property. It also has, it is able to identify corrupted participants. So if anyone deviates from the protocol, then they'll be identified. And the scheme has a security proof along with it. So I first want to talk about ECDSA in general, rather than the specifics of threshold ECDSA. This will help us to understand some of the concepts that come up in this talk. So I'm going to assume that the key generation protocol has been completed, and out of that there is a private key that we're calling A and a corresponding public key. So in the signature protocol, it takes the private key as input along with the message, and it outputs these two values that we call R and S that correspond to a signature. So what the signing protocol for ECDSA does is it simply computes these two values. And it does that by first randomly generating a value K, and then finding R from K times G, where G is the generator of an elliptic curve group. Then in order to compute S, you first need to take the hash of the message that we'll call E, and then you can compute S using the inverse of the random ephemeral key. Then that's multiplied by this bracket, which is the hash of the message E, added to the private key times the value R that has been computed. So it's important to note that, of course, it's we want A to be secret, that's the private key, but in order to keep A secret, we also have that K very certainly needs to be kept secret as well. This will be important in terms of threshold signatures. Okay, so let's talk about what a threshold signature is. So we describe a threshold signature scheme as a T of N signature scheme. And that means that if you have a group of N participants, then any of these capital T participants can, any T of these participants can generate a signature. And it really can be any of the, any subset capital T out of the N participants. There's no restriction. So in the first scheme, the scheme that was created by Gennaro with collaborators in '96, it has this property where the number that are needed to compute a signature is different from the number that is needed to compute the private key. So if we take a simple example where we have N equal to 6, we have 6 participants, and we want to require that 5 people can generate a signature. It could be any 5, it doesn't need to be this set of 5. And in this 96 scheme, the first scheme, given these 5 participants needed to create a signature, you actually had this possibility that actually 3 of them could compute the private key. And it also was that it's not possible to have this requirement of 2 participants to create a signature. It must be 3 or above. So then that enables us to define this concept called threshold optimal. So a threshold optimal signature scheme is when the number of participants that are needed to create a signature is the same that are needed to compute the private key. So this capital T, where that is those that are needed to sign, is the same as this small t plus 1, which is those that are needed to compute the private key. So how do previous schemes achieve this concept of threshold optimality? They do something called multiplicative to additive conversion. So this uses something called homomorphic encryption as well as zero knowledge proofs. So this is a protocol that's done between 2 participants. So we take participant Alice and we take participant Bob, and they start with a value, for example, alpha, with a subscript AB, and Bob has a value kappa with a subscript AB. So in this protocol, alpha AB and kappa AB is not corresponding to the shared secret, but rather it's Alice's part of the shared secret and Bob's part of the shared secret. So in order to compute the multiplication of the private key and the ephemeral key, this process needs to be done on a with every pair of participants. So Alice and Bob as an example, but if you add in a third participant, then Alice also needs to do the same thing with the third participant, Charlie, and Bob also needs to do the same thing with Charlie. And then the result is that if you add all the results of these one-to-one communications, then you can find the multiplication of the private key and the ephemeral key. So we have, just to describe this multiplicative to additive conversion, we have that Alice starts with this her corresponding alpha value, and Bob starts with this kappa value. And what they want to do is find a value x and y that results in, has the same value as the multiplication between Alice's starting value and Bob's starting value. And in the end, Alice will know x and Bob will know y. And then this x and y becomes a part of the sum that's used to compute the multiplication of the private key and the ephemeral key. So just to emphasize this, if we take an example of 4 participants and we have 3 of them can compute a signature, so it's threshold optimal and 3 of them can compute a signature. So we first have these 2 participants, Alice and Bob, that communicate to compute the multiplication. They also have to do the same thing with the third participant, Charlie. So they all have to have this one-to-one communication, and each of these one-to-one communications uses the homomorphic encryption and zero knowledge proofs, which means that it can become quite expensive, especially for larger schemes. Okay, so now let's talk about this paper, Efficient Threshold Optimal ECDSA. So similar to ECDSA, it has 3 algorithms, so key generation, the signing algorithm, and then verification. So it's based on the 96 scheme and makes a slight modification to that scheme, just noticing a simple trick. As a reminder, the ECDSA signature is this value R and S is defined to be K inverse multiplied by these brackets. And the problem that's been, the thing that causes a challenge around this threshold optimality is the K inverse times A. So if you expand out these brackets, you find K inverse times E plus K inverse times AR. And you notice that the second term with the K inverse times AR, where you do this multiplication of shared secrets, is message independent. So what is proposed then is to pre-compute this message independent term when all participants are present. And in order to do the computation, you still need 2t plus 1. If you pre-compute this term and then wait for the message to be received, then once the message is received, you only need t plus 1 participants to be involved in this non-interactive signing. So in the final non-interactive round, we have the same number of participants that are present as those that would need to come together to compute the key itself. So as mentioned already, any subset of these t plus 1 participants are able to sign in the last round, which is the first time that this property has been achieved for a threshold signature, threshold optimal signature scheme. So in the following, I'm going to go into a bit more detail, and I'm going to do an example of a 2 of 3 scheme. So let's first consider key generation. So this protocol is a method for participants to compute a shared secret, and this is using a known protocol that was published in 2007. And the result of this protocol is that each participant has a share of the private key, and all of the participants explicitly know the public key, A times G, the group generator. So very common is that these, very commonly known is that these shares are actually points on a polynomial, and the secret of the shared secret is actually defined at the value x equals to 0 on this polynomial. So participant 1 in our example of the 2 of 3 scheme has knowledge of the polynomial that corresponds to the private key where x equals to 1. So participant 1 knows the result of the polynomial at x equals to 1. Then similarly, participant 2 knows the polynomial at x equals to 2, and 3 the same thing at x equals to 3. Then, so given that each participant just knows 1 point on this polynomial, it's not enough information to know anything else about the polynomial, but collectively they have the knowledge of the polynomial. And this is where we see that even though we have this shared secret, this private key A, no single participant has knowledge of that private key. It just exists through some collective knowledge, although no one explicitly knows it. So given the shares on polynomials, what you can do is actually do various computation on the shares. So if you have 2 shares, you could do a combination, 2 shares on different polynomials corresponding to different secrets. Then you could do a computation, do any computation such as addition or multiplication. And if you have enough points, enough results of this computation, the computation on the shares, then it's possible to compute the result of the computation on the secrets themselves without actually revealing the secrets themselves. So this is how the 96 scheme, and this is how the scheme I'll be showing today, achieve this threshold signatures. They take shares on polynomials and do computations on these shares without actually revealing the secrets themselves. Okay, so then the signature protocol. So we've done the key generation protocol and the output is private key shares. Then if we want to assign a message, then the participants, they first will compute the shares of K, and they'll do that in the same way as they've computed the shares of the private key. So this is a really key point that I wanted to emphasize, that K also needs to be a shared secret for that reason that I said previously, that if any of the participants know K, then they can immediately compute the private key. So K must be a shared secret. Then they also need to do some computation to compute K inverse, which was described in the 96 scheme. And then they similarly must compute R, that forms part of the signature. And the next thing they do is they take their shares of K inverse, they take their shares of the private key, and then each participant multiplies the shares together. And then they finally add shares of a third shared secret that we're calling beta, that they've generated to these 2 shares, and then they're able to share this value, and then every participant can compute the result lambda. So it's really important that this third shared secret beta is added, because if you just compute K inverse times A, then once the signature is computed, it's really easy to compute the private key. So we add this shared secret to offer some sort of, to keep the security. Then once they have computed this value lambda, they pause the computation, and this is done with all 3 participants together. And then when a message is received, then the 2 of the 3 participants is able to compute the signature on that message. So they do that by, of course, taking the hash of the message to find E. Then they take their share of K inverse and their share of beta, and then they combine them with lambda in this equation S. So just to emphasize, in our 2 of 3 scheme, they first must compute the share of lambda and then broadcast this value. And then when the signers want to sign a message, so just 2 of them, and again, it can be any 2 of them, they are able to compute this value S, which is just an addition of shared secrets, and therefore only need T+1 participants. So this means that there's no one-to-one, you see that there's no one-to-one communication after the shared secret generation. So it's really, there's no kind of, it's very efficient, especially as you get to higher group sizes. And the verification is the same as if it was created by a single private key. So I won't cover this in detail. So like I said, the scheme has a security proof, and it is proven to be robust and unforgeable. So robustness is that the result of the protocol is of an algorithm is still computed if there's a certain number of corrupted participants present. And then unforgeability is that there's a negligible probability of an attacker being able to generate a signature on a previously unsigned message. So we prove that the scheme is robust and unforgeable, assuming decisional Diffie-Hellman and that ECDSA is unforgeable. Okay, so the last thing that I'd like to do is to compare with some recent results. So these offer the same functionality of this non-interactive signing. They also split their signing protocol into first a pre-computation rounds, few pre-computation rounds, and then one final round that is non-interactive. So they're all threshold optimal. And then the scheme presented today, along with the scheme by Gennaro and Goldfeder, offers identifiable abort. Then the scheme presented today is the only one that doesn't have any homomorphic encryption or zero-knowledge proofs. And that also helps to lends itself to that there's no predetermined signers in the non-interactive signing step. So any participant can sign in that final step, and that means that it offers some protection against failures of participants. Also means that it's scalable because there's no, only the first round has the one-to-one communication, and also that there's no homomorphic encryption and zero-knowledge proofs. Then they're all general schemes, general T-of-N schemes, threshold optimal. But the scheme presented today does have this restriction on n. So if capital T is equal to T+1, then it does need to be that the number of participants n is larger than 2t. Then in terms of rounds of communication, the scheme presented here has 2 rounds during key generation, which is 1 fewer than the other 2. And then in signing, it has 4 rounds, which matches the Canetti plus collaborators scheme and has 3 fewer than the Gennaro and Goldfeder scheme. Then to compare some numbers with the other 2 schemes. So the other 2 schemes, aside from the one presented today, they shared some results in their papers, and this is what it is being compared to. So the scheme that's been shared today has, after pre-computation, can create over 8,000 signatures per second. And there wasn't data to compare that value to the other schemes, but I suspect it will be a very similar timing. Then for in terms of the whole signing protocol, so just both the pre-computation and the final non-interactive step, if we take the capital T to be equal to 2, so the number of signers needed to be present equal to 2, then we see that the scheme shown today is 144 times faster than Gennaro scheme, and is 240 times faster than the scheme with Canetti and collaborators. And then we see the higher the threshold gets, the more efficient it is compared to the other two schemes. Thank you very much for listening to this talk. And if you have any questions, then please do contact me on this email on the screen.